The gas turbine engine, more commonly known as a jet engine, was first fabricated in 1907, but its origins may be traced back to 150 BC. Whilst the engineering of modern jet engines is within a well-established industry, the fundamental principles behind them and materials that enable them are easily apprehensible. There are four main stages to a jet engine. From front to back, there is intake through the fan, compression in the core, combustion, and finally exhaust through a turbine. Despite the complexity of components within the core, counterintuitively, 90% of the total air intake bypasses the core. This generates 75% of the engine's total thrust output. The remaining 10% of air is accelerated through the core into the turbine, where the energy from an ignited and compressed air-fuel mixture is extracted by the turbine. The turbine then converts this into torque that is transferred through the shaft to drive the fan. As all these components vary in size and purpose, the load scenario implicated onto the shaft is complex and may lead to bending. To minimise bending, specialised steels such as Super CMV and AirMet 100 have been developed. These super clean steels are free from non-metallic inclusions such as carbon to increase their tensile strength. Composed of a central disc and surrounding blades, the fan is the largest rotating component in the engine. It must withstand the tangential forces as well as being resistant to foreign object damage and corrosion. Titanium is a highly versatile material that is well suited to this. Its strength to weight ratio is desirable despite the difficulty of manufacturing with it. There are three main stages within the core. In reality, the proportions of the engine, core and components would be different to this exaggerated model. Initially, air entering the core passes through a series of fans that's radius decrease in proportion to the core. Separate high and low pressure compressors deal with this variation in temperature and pressure. Often they spin in opposing directions for optimal efficiency. Fuel is then injected into the combustor where it is mixed with the compressed air and ignited. The core is at its smallest diameter here to maximise the air-fuel mixture that is achieved in this constrained area. The energy released from ignition is absorbed by a series of turbines. These turbines quickly increase in diameter as stress and temperature variations are high here. Channels through the blades provide a thin layer of air for cooling. As temperatures vary in the compressor, different materials are used for the high and low pressure compressor. Near alpha titanium is well suited to the low pressure compressor where the temperature is still relatively low. Nickel-based alloys are used in the high-pressure compressor as their strength at temperature begins to overtake titanium's. There are no moving parts in the combustor, so material selection prioritizes thermal and refractory properties. Like their counterparts, nickel-based superalloys have improved heat-resistant properties due to their denser atomic structure. CMCs have extremely high melting points and an ability to maintain their strength-to-weight ratio at temperature. Temperatures in the turbine are still high, so engineers may choose to use nickel-based superalloys again here. Gamma titanium aluminium was developed to have a very low density without sacrificing the strength of titanium. A ceramic coating on the blades further improves its heat resistance as it reduces the temperature gradient within the blade. An array of specialised materials have been developed to meet the requirements of a jet engine. This area of engineering is always developing and pushing the boundaries of what is possible. The relatively simple concept of a jet engine has developed into a sophisticated piece of engineering that is used consistently on a global scale in the modern day. As industry moves towards more environmentally friendly processes, efficiency and performance of a jet engine is key. Engineers have a variety of ways to tackle this problem, such as developing new materials. This allows for lighter engines that require less fuel and enables operation at higher temperatures that increases efficiency.